Yesterday we looked at the binary class classification. I forgot to upload these files, I think. I'll do that today. No, if you guys check and cannot find some file, right, let me know. So I'll do that. Sometimes I'm forgetting how to upload these files. So we have got to know how to build a decision tree classifier. But in real time, we may not build decision tree classifier in our projects. But these are used internally, and we need to understand these hyperparameters. Right? Min sample split, min sample leaves, right? All these hyperparameters we need to understand, and anyway we can play with them using the grid set CV. Now we'll understand the classification regression. So far we understood how the split is happening on a classification data set. Decision trees can be used on regression also. It is very simple on regression. Now I have taken the hitter data set. It's a cleaned data set, so I said hitter tree. It's a baseball, players data, the player name, and how many times he batted and how many hits and how many runs, how much salary the person is getting. So based on this data, we need to decide salary. So to make it simple and understandable, what I did is I have taken hits, years and salary only. Based on number of hits and years, we'll try to decide if the person's salary. If we have to do that, right? In decision tree, what it will do is, it will split data into multiple regions. What is the region? So years less than 4.5, the salary mean, right? It will take and it will predict as that salary. So here the data is split into 3 regions. One region is years less than 4.5. That is one region. All the people whose experience is less than 4.5, the model will predict 225.883K as salary. Okay. If
is that 4.5 is median?
No, it is just a number. How to choose that number we'll decide.
Okay, sir.
It's a threshold, right? So in our in our classification data set, we right based on some metric we chose a column.
Yes, sir.
So here also we'll choose a column and we'll choose a threshold also based on some metric. We'll see that. That's an algorithm. Actual algorithm. How how it chooses the threshold and how it chooses the column is an algorithm. But at a high level, if you have to understand how decision trees are working on regression problem, it chooses some threshold on appropriate column and tries to put the threshold and predict. So suppose we built a decision tree model which is like this: years less than 4.5, all the people who are having less experience will predict their salary as 225.83. If the years is greater than, right, then we look at hits. If hits are less than, all those people who are greater than, who are having greater than or equal to 4.5 and hits less than 117.5, we predict their salary as 465. Okay. If years greater than 4.5 and hits greater than or equal to 117.5, then we predict their salary as 949.17K. How did we got these numbers? These numbers are the average of all the people who are falling in this region. Okay, when I say region, 4.5 years and less salaries, less than 4.5 years salaries, I have taken target variable and took mean and predicting that as the prediction for all those people who are falling less than this age and who are greater than this years of experience and less than this many number of hits. I have taken mean of it and predicting that mean as the prediction for all those records, and again for other condition also. So decision tree works on regression like this. We took mean of the target variable for this condition, we took mean of the target variable for this condition, we took mean of this target variable for this condition, and then we are predicting, for all those records falling in this range, we are predicting this as the salary. In this range, this as the salary. In this range, this as the salary. That's how it works. Any questions? At a high level, that's how it works on regression. Any questions?
No, sir. Simply to understand.
Okay. So the model will predict salaries of the players based on below conditions. If years of experience less than, predicted salary is equal to average salary of players with years less than this experience. Now, if experience is greater than, then we look at the hits and then try to take the average salaries of those ranges, whatever I explained. The algorithm consists of a series of splitting rules. This is splitting, right? And starting at the top of the tree, one can interpret these splitting rules as shown below. Regions, we can assume them as regions. Less than 4.5, one region. Greater than 4.5, two regions we have. Right? R1 and R2. So whole data is splitted like this, and for all these data points, the prediction is going to be the mean of all these data points. For all these data points, the prediction is going to be mean of all these data points. For all these data points, the prediction is going to be mean of all these points. That's how we did it. Okay. These three regions can be written as R1, R2, R3 are known as terminal nodes or leaves. On a tree, these are the leaves or terminal nodes. Okay. Terminal nodes. The terminology you need to remember. R1 is equal to X for all years less than 4.5. R2 is equal to X for all years greater than whatever. Right. So this is mathematical notation. The points along the tree where the predictor space is split are referred to as internal nodes. So in this range, whatever the data points are falling are all called as internal nodes. Terminal nodes, leaves, terminal nodes or leaves is same, the leaves, and internal nodes are the nodes which are falling inside that whatever. So this is how it works. X less than or equal to some condition, split the data. X2 less than or equal to some condition, split the data. Again, X1 less than or equal to some condition, split the data, like that. So it is splitting the data into multiple subsets. Even here also it is splitting the data into multiple subsets, but based on conditions it is doing, the numerical values it is doing. Okay. So roughly speaking, there are two steps. Okay. I think the same thing. Right? So how to select the best predictor? So that's the question actually Bala asked now, right? So how to select the best predictor and the threshold also. Okay. The value in year less than for the predictor at each node. We take top-down greedy approach that is known as recursive binary splitting. Recursive binary splitting is the approach we call it as. The approach is top-down because it begins at the top of the tree, at which point all observations belong to a single region. Initially, all data points belong to single region, and then successively splits the predictor space. Each split is indicated via two new branches. That's where we call it as binary split. Okay. Further down on the tree, it is greedy because at each step of the tree building process, the best split is made at that particular step. It is not going to consider what happens if I do the split and in future, maybe after 10 splits, what happens? It is not going to consider. At that particular moment, whatever is more appropriate, that decision it will take. Maybe because of that, in some cases, it may go into a place where the split may not be appropriated in more downer spaces, downer the areas right here in the downer areas. Rather than looking ahead, and picking a split that will lead to better tree in some future steps. So it is not going to consider future steps and do the split. Current step only it considers. So it is binary split. So recursive binary split, how it works, the algorithm we are trying to see. The goal is to find R1, R2, and so on Rj that minimizes RSS, residual sum of squares. Right? You remember the formula, right? RSS. So RSS means you try to make predictions for each range, right? The regions are there, Rj regions, R1 till Rj. In this case, 3 regions are there, right? So in this region, you make prediction. What is the prediction? Average of all the target variables. In this region, prediction is average of target variables. In this region, average of the target variables. We have predicted values. We know the actual values. Take the differences, right? The squared distances between the actual values and the predicted values. Here, and then sum all those 3. That is the second sigma. There are j number of regions, 3 regions. For each region, you are calculating the residual sum of squares and summing it. Okay. The goal is to minimize that, right? So you may actually do a split maybe at 10, right? For the region 1, you may do a split at 10, but that split may give you more error. So what you do, you randomly choose one split and try to calculate the error and then try to adjust that. Okay, that is the recursive binary split. So where YRJ is the mean response of the training observation. So we know that, right? YRJ is the prediction, right? I have explained that. We consider all predictors x1, x2, and so on xp. What are predictors? x1, x2, and so on xn. N number of predictors are there. Y is the target variable. And all possible values of the cut point S. What is cut point? The threshold. 4.5 is the cut point. Okay. For each of the predictor. For x1, we'll take one cut point. For x2, another cut point. For all the p columns, we'll take different cut points. Okay. And then choose the predictor and the cut point such that the results of the tree has the lowest RSS. It is recursively, we take x1, a cut point, and try to split the data and calculate the RSS. Again, for x2, we'll take another cut point. Like that we'll do. R1JS, x such that x less than s. That is the cut point. And R1, R2, right? R2, like that. So, and we seek the value of j and s that minimizes the equation. So this is the equation. So every time we are making binary split, right? On the binary split, we are trying to calculate the error. For x1, we are doing one cut point we chose, we calculated error. Second cut point we chose, we calculated error. Third cut point we chose, calculated error. Like that, many times we do. Wherever we get that less error, we'll keep that cut point and the column. So first column, best cut point, we'll put it aside. Second column, best cut point, put it aside. Third column, like that for all p columns, we'll calculate. Whichever gives you the least error, we'll take that column and that cut point as the current split. Got it?
But RSS is a residual sum of squares?
Residual sum of squares.
Okay.
Of all the regions.
Okay.
Okay. We repeat the process looking for the best predictor and best cut point in order to split the data further so as to minimize the RSS within each of the resulting regions. However, this time instead of splitting the entire predictor space, we split one of the 2 previously identified regions, right? First we made this split. Then in this region, we'll do 2 splits. In this region, we'll make 2 splits, like that. And again, after doing this, we'll take this region and make it 2 splits. This region, make it 2 splits, like that. So going forward, the number of iterations will reduce. So initially, the iterations may be more, and we may have to look into all columns. But going further down, the iterations will reduce. We now have three regions. Again, we look to split one of these regions further, so as to minimize the RSS. The process continues until a splitting criteria is reached. For instance, we may continue until one region contains more than 5 observations. So no region contains more than 5 observations. No region, sorry. So that means we will do the split until one region has got 5 data points. Okay. So that is the process in a regression setup, decision tree regression setup. Any questions? Simple, right? It is. Recursively splitting and trying to see whether error is low or not. Find the split point, cut point.
Sir, it goes for more generalization, right? So if we have to go to, for example, less than 4.5 is there, that will be for 1, 2, 3, everything. So if we want again specifically, then we have to go on that 4.5 itself, on the same attribute, we have to go for another cut point.
Yeah, maybe. Your question is like this, right? We did split on x1. Do we have to do split on x1 again?
Yes.
Yeah, see this here. Right, we did x1 split here. Again, we are doing x1 split only. If that is the best, right, we should be doing it.
Okay.
That is the best we should be doing it. Any other questions? So this is a decision tree regressor, the class, and I have taken housing price dataset. This dataset I did not took. Okay, that's very simple. So I have taken a housing price dataset. I splitted data into train test. Then I applied a decision tree regressor and fitted the model. When I fit the model, it will find those rules, right? If else conditions, and predicted, calculated the error. I have got 74%. I used randomized search CV. Do you remember randomized search CV? Randomized search CV actually takes 10 combinations from total. It's a default value. Right? If you specify more than n iters, more than 10, right? It will take more than 10 combinations and choose the best. So I have got max depth 4, max leaf nodes 66. So when I calculated, it improved a little bit, but it's a overfitted model. So randomized search CV, I never found it very useful. Maybe manual analysis is better. Manually trying to play with the hyperparameters and find the best range, and then use grid set CV with less number of range is good. Okay, that is decision trees. If we are all good, right, I'll move on to ensemble models. Okay, let us move on to ensemble models. If time permits, right, I'll try to explain recommender systems also in this course, because anyway I have to write that, prepare the PPTs for recommender systems. Once it is done, right, I'll explain, or we'll anyway give it in that AI learning, right? So you guys can look at it. And in future, whatever new content we build, we are going to upload it to AI learning. So you will have access to that whole thing. And one more thing, you guys are taking the integrated course, right? So you will get free access to the deep learning also on AI learning, so that whatever we newly add in there, you will get it. Okay. So AI learning is going to be a huge advantage for me and you both. I don't have to talk like this for every day, and for you will get most recent updates on the technology. Any questions?
Sir, one doubt.
Yeah.
In decision tree regression, the first column on the topmost on the root node, whatever the column, that also will determine, will impact the result, right? So
yeah, no, will impact the result, and we are choosing the best column and best cut point.
okay.
Every time we do a cut, we do a region split, we are looking at best column and best cut point. While doing the first split, we look at all columns. We'll take X1.
Okay.
Right, in X1 we'll take different cut points,
Okay.
and look at RSS.
Okay.
X2 again different cut point, look at RSS. X3 again cut points, different cut points, look at RSS. Whichever column gives you a good cut point at, good RSS, less RSS at cut point, we'll choose that as the column to split. Every time we do it, we'll look at all columns.
Okay.
Even in our classification also, we were looking at all columns, but I actually showed that because I was a little lazy in calculating, right? That notes preparation takes lots of time, at least 2-3 days it takes. I'll speak here for maybe half an hour or 1 hour, but it takes more time. So I was lazy and cannot do it, so I eliminated some columns and tried to do calculation. Generally, already splitted column may not come as a split column again, generally. May not. No, it's not hard and fast rule, but in general. Okay, so let us jump in and try to understand the ensemble models. What are ensemble models? So far, what we have seen is we are using only one model, one algorithm to predict, right? Where we have taken either logistic regression or SVM or decision tree, and or KNN to build a model, train a model, pass your train set and train a model, and then pass your data and making prediction. But in ensemble models, we will train model 1, maybe logistic regression, model 2 SVM, model 3 decision tree. We pass training set to three algorithms and train 3 models, and then pass our new record to 3 models and make them predict. We'll make a decision based on 3 predictions or 10 models, 10 algorithms, 10 models, and take 10 predictions and take decision based on voting, the majority voting. Okay, majority voting classifier is called as hard voting classifier. There are 2 ways of doing this ensemble model. One is based on majority voting. Here, the first model and third model are saying 0. Out of 3, 2 are saying 0. So we predict 0 as the outcome. So that is called as majority voting or hard voting classifier. And there is soft voting classifier, which actually looks at the probabilities rather than zeros and ones. Okay, so this is ensemble model, and deep learning models are more advanced ensemble models, more complex and advanced ensemble models. Okay, so when we go into deep learning, right, most of the machine learning algorithms may not be that useful in a big data setup. Okay, so deep learning is very crucial and very important, and in future, right, if people know and people have got that much of a rigor to learn, deep learning is going to solve many problems. Okay, so here we have 2 kinds of voting classifiers, the hard voting and soft voting. The first one takes the majority voting and predicts. The problem with majority voting is that maybe this model made it 0 because the probability is 0.499999, right? The threshold is chosen as 0.5 and the predicted probability is 0.4999. And here also, it may have predicted as 1 because the probability may be 0.51, right? Maybe all 3 should be saying 0 or all 3 should be saying 1. If you take 0.49 as the threshold, all 3 would be saying 1, and you may have got one there. So if you consider probability, right, it's going to be more appropriate. So that is called as soft voting classifier. So if for some reason the first model and third model are became 0 because of the probability is 0.49. But the second model is very confident that the record belongs to 1. In that case, if you take the average of 3 probabilities, you will get 0.66. As a whole, the probability is greater than 0.5. But if you look at the hard voting classifier, you got 0. But on the soft voting classifier, you got 1. Right? The probability of class 1, you got 1. So soft voting classifier is better because some models may be more confident in making prediction, either it is positive or negative. Right? Their confidence will be considered when you take average of the probabilities. Got it? The difference between soft voting and hard voting?
Yes, sir.
Any questions? Anybody else? Simple. Not just 3 models. You can take 100 models also here. That is called as ensemble model. And there are 2 ways. One is majority voting, like Indian voting, right? And then Indian voting or any democratic voting. And then the second one is the probabilities. So maybe the score should be calculated for elections also. That way, it's going to be more better, I think. But score, how to give score, people doesn't know. That's a big problem, right? So that's okay. So, in SVC, if you want the algorithm to do work as soft voting classifier, right, you need to specify voting is equal to soft. Then only it will work. Rather, it will not calculate probabilities. By default, SVC will not calculate probabilities. It will calculate the decision scores only. So if you specify the voting as soft, then only it will calculate probabilities. So here I have taken a data set, right? Random forest, voting classifier, logistic regression, and SVC. Right? Here I have built 3 models, or I have created 3 algorithm instances: logistic regression, random forest, and SVC. And I have taken voting classifier and then gave estimators. Estimators as a list of tuples. The first is the name and the algorithm, name and algorithm, name and algorithm. The voting I said as hard. By default, it is hard. Okay, even if you don't specify it as hard, it's going to be hard. Hard voting classifier, and train the model. When I train the model, what happens? The X train, Y train will be passed to logistic regression, random forest, and SVC 3. And when you make prediction, right? If you look at this classifiers, I individually tried to predict, and I used the voting classifier and predict. Here, individual predictions are printed first, right? Each individual, classifier, one gave points, 86%, another 87, another 88. But altogether, the voting classifier, when I predicted and calculated accuracy score, it actually gave me 89%. Okay, that is hard voting classifier. If you have to do soft, right, you need to specify voting as soft. And again, if I looked at the individual predictions and the voting classifier prediction, even voting classifier also I took in the for loop, right? I have got 91%. So the 2% increment is there in prediction. Then I used soft voting classifier. The voting classifier is a class which takes multiple, algorithms as input. Got it? This is how you do the ensemble model. Ensemble model is very easy, right? When you know other concepts, ensemble model building is easy. The total process will not change. The data pre-processing, splitting data pre-processing, making the data set ready, then building a model and checking accuracy. If the model is not working, maybe you should do fine tuning. Maybe here you can pass the hyperparameters to each of these algorithms and make them the best, or individually you find out the best models and try to use them here in the voting classifier so that it becomes even better. Got it? Any questions?
No.
Okay, good. So bagging and pasting and random forest are also ensemble models. Okay, bagging and pasting are same. Only minor difference is there. Minor difference. So in bagging or pasting ensemble model, we use same training algorithm, but train them on different random subsets of the train set. Random subsets of the train set will be different. Okay, bagging. When sampling is performed with replacement, we call it as bagging. When sampling is performed without replacement, we call it as pasting. What do you call sampling with replacement as? We looked at resampling techniques, right? In that, we have seen one sampling technique with replacement. What do you call it as?
Bootstrap.
Yeah, bootstrapping. Good, right? Interviews, they'll ask these questions. Okay, bootstrapping, right? So this is how it works. Suppose that your train set is this, a small train set I have taken 1, 2, 3, 4, and there are some values. In bagging, bootstrapping is the sampling technique. What it will do is, it will actually sample with replacement. I have taken 3 records and trying to reproduce 4 records there. What is sampling with replacement? We'll take 100% data and take 66.7% out of it and reproduce 100% data by replacing with the existing records. Okay, so I took here 1, 3 and 2 and replaced 3 again so that I can generate 4 records there. Okay, 70% only I take, because here I cannot take 66.7, and then build a tree model. Okay, in bagging classifier, you can either do tree model or logistic regression also. You can take logistic regression algorithms also here, but all the algorithms are homogeneous. Okay, here heterogeneous ensemble model we have created here, right? We have used different algorithms in same voting classifier. This is called as heterogeneous ensemble model. The bagging, pasting, and random forest are homogeneous ensemble models. Even deep learning, maybe kind of deep learning, I don't know, because target variable, the output layer will change. Sorry, but the bagging, pasting, and the random forest are homogeneous ensemble models. Okay, so the second sample, so you specify how many trees it should be building. If I say 500, if I say 3, right, it will build 3 models. So second, I have taken 1, 2, and 4. 4 I replaced. Third, 1, 2, and 4 I replaced 1, and then built 3 models. And when a new instance comes in, right, I passed these 3 models, and took the hard voting classifier is what it works. So the bagging classifier, once all predictors are trained, the ensemble model can make prediction on new instance by simply aggregating the predictions of all predictors. The aggregation function is typically the statistical mode, right? Statistical mode, right? Mode is the function there. The most frequent prediction, just like a hard voting classifier. This is a hard voting classifier only. For classification are for average for the regression. Okay, bagging and pasting are scalable. Predictors can all be trained in parallel. Here, if you see, this model can be trained on one machine, this model can be trained on another machine, and this model can be trained on another machine, because these models are independent of each other. We took different samples and passed data and then trained the models, right? Via different CPU cores, and similarly, predictors can be made parallel. Predictions also can be made parallel, because if the models are present on different servers, right, you can pass the data to different servers and make predictions and come back. This is one of the reasons why bagging and pasting are such a popular methods. They scale very well. In pasting, you just do sampling but no replacement. I have taken 1, 2, built a model. I have taken 1, 4, built a model. I have taken 3, 4, built a model, like that. Okay, pasting is small data sets you get, because sampling only you do, no replacement. But is there any use of replacement here? Can you guys guess any use of replacement? Bootstrapping use? See, I was having this question when I was learning. If you have duplicate records in your data, is it going to harm your model? That's the question.
Duplicate records will harm.
Ilham? Okay, how many agree with that statement? Anybody disagrees with that statement? No disagreement. I'll say one thing. If a particular class records are very rare and you replace them, or you actually try to copy paste more records of it, the algorithm will find the pattern. It actually helps, right? If you have 99% of the data belonging to one class and 1% data belonging to another class, you can actually copy paste that 1% data and build a model so that the model will understand pattern in that data, in that rare class. In our anomaly detection algorithms, there are techniques like SMOT, which actually tries to generate synthetic data on X side, which is of same pattern, and Y variable it takes the rarer class. I'm getting it right? It is like bootstrapping only. It's like copy pasting only. So here the bootstrapping helps. If the given the whatever record here, I replaced 3 twice, right? If the 3 is the rarer class in your data set, if you replace it, it helps. Sorry, if you copy paste the data and try to build a model, the model will understand pattern inside that rarer class. Okay, bootstrapping is helpful. Is helpful when the data set is imbalanced. Okay, so that is bagging and pasting. Okay, how to build a model? The bagging classifier is a class which actually takes another class as input. I have passed a decision tree and an estimators I have specified 500. It is going to build 500 trees. And then bootstrap is equal to false, I said. When I say bootstrap is equal to false, right, it becomes pasting. Okay, when I say bootstrap is equal to false, it becomes pasting. It is not going to do bootstrapping here. Okay, the terminology is very important. If you don't know what is bootstrap, resampling technique, you don't understand what is happening here, right? N jobs is equal to -1. We left it to the computer. How many processors it want to take, it can take. Okay, you can give a number of processors here. Random state 42, you all know. I fitted, and this is a pasting algorithm, predicted, and then looked at the accuracy score at 91% on train set, test set it is. Okay, and then I have built a decision tree classifier, just a decision tree classifier. I have got 85% accuracy. And the bagging classifier with bootstrap is equal to true, and logistic regression I have taken, not the trees. So boosting and pasting can be done with any algorithm. Random forest can be done with only tree algorithms. That point you need to remember. Okay, max samples. So this is a good point. Max samples I have given 100. That means when I am actually trying to do sampling, right, I will take only 100 samples. Even though there are 1000 records, I don't care. 100 samples I take and build a tree. 100 samples I take, build a tree, like that I'm going to do. Okay. So there is a concept called out of bag evaluation. In bagging classifier, if you say OOB score is equal to true, it is going to give you out of bag sample error. What is out of bag sample error? Here we chose 3 records and 1 record is left out, right? I built a model on 3 records. I am testing it on the left out record. That is like cross validation data set, right? No need to do k-fold cross validation here. If you say OOB score is equal to true, it is going to give the out of bag error. Whatever the records left out, the model is going to be tested on those left out records, and then you get that score. So that is one more advantage in OOB evaluation. Okay, so our OOB score is equal to true. We can specify. So the points, did I cover everything? I think so. The accuracy score I have got 91% and OOB score also 90%. So the model is working good. That OB decision function will give you the what you call it as the probabilities. Okay. So that is the bagging and pasting. Any questions? Any questions? No, right? Good, right?
The probability one that you have shown just now, sir. So that one.
This one.
Yeah.
Yeah, this is like you are looking at predict proba and decision function, right? Decision scores. OOB decision function gives you the cross validation data set probabilities. The left out record the probabilities. Okay. And anything else I forgot here? No. So pasting is created using bagging classifier only. If you say bootstrap is equal to false, it's going to be pasting. That's it. So that is bagging and pasting. Now random forest. It is also simple. Random forest classifier. Oh, 1 point I forgot. Okay, 1 point I forgot. In our decision trees, we saw that decision trees are tend to orbit, right? Why is it orbiting? Why is it orbiting? Can somebody explain? Oh, how bagging, pasting can help in reducing the orbiting on decision trees? Can somebody think about it? Okay, keep thinking, right? Anyway, I'll explain, but keep thinking. After
decision tree, if a perfect node is not found, perfect matching node, that will go for in a testing data set, it will go for overfit. Yeah, I know you are kind of there, but just think about it. I'll explain random forest and then we'll come back to this. This is one of the very important interview questions. Okay, how can the ensemble models solve the overfitting issue in decision trees? That's the important question. Okay, so the random forest is an ensemble model which uses decision trees. When you say random forest, there is no way that you can specify the classifier, okay, or regressor. Okay, so internally it uses decision trees only. How many estimators? Max leaf nodes, n jobs, and all these are hyperparameters. You pass your x and y, you predict, you look at accuracy scores, right? So in random forest, we have got feature importances. So if you actually build a model, right? If you fit a model and then say feature importances underscore, you will get scores for each feature. When you sort them in descending order and map it to the feature, you see this. There are some features which are important in our digit recognizer data set. Pixels, these are all, right? If you look at it, so by some place, right, they are becoming zero. Almost the importances are becoming zero. These pixels are not so useful. See this? These pixels are not so useful, right? So I can take only those particular, records with highest importance and then build model and make the model work good also. Okay, so you can actually find out if it is a text data set, right? You can find the important words after building the random forest algorithm. So here, while doing random forest algorithm, you can specify number of columns also. Here, n samples I specified, right? Max samples I specified, right? Like that, you can specify max features also. That's an important thing. Okay. Whatever points I am highlighting are important. Give me 1 second. Let me open the random forest one also. Right, random forest classifier. Here bagging classifier I opened. Here random forest classifier I am opening. And we are going to look into some hyperparameters here. Right, n estimators. The number of base estimators in the ensemble. Right, n estimators. So how many models it should be building? Max samples. How many records it should be
taking a sample each time, right? Here in this diagram, out of 4 records, I have chosen 3. But by default, if you don't specify anything, right, it's going to be max samples. Default is 2. It will take 2 samples. No. Split it is. Max depth criteria. No. What is this? Okay. Bagging I need to go. Okay. So max samples is how many samples? No, it will take. Default is 100%. It will take. 1.0 means 100%. The max features, all features it will take. If you specify, 0.5, right? Only 50% samples it will take. By default, in random forest, it is going to be square root of n sample, number of features. Estimators, bootstrap. You can specify bootstrap is equal to true here also in random forest also, right? In random forest, if you say bootstrap is equal to true, it will do sampling with replacement every time it samples. OOB score, n jobs, class weight, max samples, and how many samples it should be choosing, and max features will also be there. See this max features. Auto means square root it will take. Square root of total features, right? Log, square, you can specify whatever the way you want it. So now can you think we are actually using square root of n number of features for each tree building. Now if I am confusing you, please stop and ask me. In random forest, I said I need to build 500 trees, and by default the max features is square root of n, right? In this data set 784 columns are there. Square root of 784, I don't know how much it is, right? So that many number of features we are taking every time we build a tree. 500 trees I am building. No, maybe 30 columns we are taking every time we build a tree. So is it going to solve our overfitting issue? When you take less number of samples while building the trees, 500 trees, and then less number of features, is it going to solve our overfitting issue in decision trees? That's a question. Guys, can you think? Can you think? Some data set we don't care about why, right? If we have this kind of a data set, if you want to build a tree, right? X1 you took, it is A, right? You are splitting the data into what? It will be AX, AY, right? Rest all will come here. AX, AY will come here. And then BY, BX, CX will come here. Now if you do a split on X2 is equal to B, right, it will be like CX will come here, right, and BX, BY will come here, right? If you have, I think we need to put the target is 1, 1, 0, 0, 1. Right here, AX, AY, this is not pure, right? This is not pure. Dynamically, I'm trying to do this. Maybe I'll make it pure. So here BX is 0, Right. This is 1. Okay, and Cx is 1. When I splitted it, it became 1. Bx, By. I should have done it on x2 column, right? X2 column is x and y, right? So I should be taking x here. So Bx, Cx will come here. I'm dynamically trying to build a tree, sorry. So if I take x2 is equal to x, what will happen? All x's will come this side, right? Bx, Cx will come here. What is Bx? Maybe I should put 1 there and C 0. 1, 1. And then here B by 0. Okay, like that. If your tree is like this, right? If you get a Cy, will you be able to predict? If you get Cy, will you be able to predict? This is decision tree. Okay, will you be able to predict? Cy, will you be able to predict with this decision tree? Guys?
No.
Huh? No, yes?
No, sir.
No, sir.
No, right? Huh?
No.
No, we cannot predict, right? Because this record is not there in the data set, and while splitting also you will not encounter it. X1 is equal to A. No, it is not. So it will come here. So X2 is equal to Y. It will go there. But you don't have Cy. Only By is there. You cannot predict, right? So that is the overfitting issue in decision tree. But if you build 2 trees, right? You take X1 and build 1 tree, and X2 another tree. Random forest. Okay. In random forest we have two models. 2 trees we are building. 1 tree is based out of X1, and X1 is equal to A. Right? It will be Ax, Ay, right? Some decision, right? Ax, Ay is 1, 1. Okay. All B's and C's will come here, right? So Bx, By, Cx will come here. This record is not there. We need to predict that. Okay. So the target variable is 1, 0, 1, right? And only X1 we have taken, right? So again, X1 is equal to B. X1 is equal to B. So we splitted this as Bx, By, 1, 0. So forget about the purity for some time, right? For C, it is 1, right? C, it is 1. Cx, it is 1. So this is 1 tree, and another tree for the decision tree, right? It is going to build multiple trees, right? I said n estimators is equal to 2. For X2, I am building another tree. If X2 is equal to X, I am building. Right? All X's will come one side. What is X? So Ax, I think I should not be taking X2 here, right? Yeah, I should not be taking X here. So give me 1 second. When I am building a tree with the X1 column, I should be considering only X1 column, right? So X1 is equal to A, right? So that's going to be A and 1, right? Both A and 1 only we have got. This A, 1, 1 we have got. So B, 1, B 0, and C 0 we have got. Now again, if you split it on X1 is equal to B, you will get B1, B0 as subtree, right? And then for C, you will get C0. That's the tree we built for only X1 column. For X2 column, X2 is equal to X. That is Now for x you have got 1. For x we have got 1, x is 0. So x1, x0, we have got 2. Right? And then for y, both are 1. Okay. So now if you use this tree, this tree and this tree to make prediction, it's an ensemble model, right? You got c and y you need to predict. For x1, you pass this into this. It is not a, so it's going to come this direction. So let me take green color. It will come this direction. Okay, and then it will come this direction, and c is equal to 0. So for c, the prediction came as, for this record, this tree predicted 0. Okay. When you pass y, it is coming, it's going to come this side. It's going to predict 1. If you have one more model, right, which is predicting maybe 1, you can predict it as 1, because 3 different models we have got, and 3 have, out of 3, we have got 2 predicted 1 and 1 predicted 0. That's how we can solve the overfitting issue. Here, you cannot predict it because it's only one decision tree model. Using random forest, you have built multiple models, and those models are built on subsets of the data. Either it is column subset or row subset, so that you will get many combinations. Right? I've dynamically writing this thing has created maybe a bit confusion. In AI learning, I'll create a clear example. Okay, maybe watch there. But did you get the essence there? Because of splitting the data into multiple, subsets, we have got multiple combinations there. Because of those combinations, we are able to find only C in one tree, only Y in another tree. We are able to make prediction. In combination, we cannot find it. In this whole tree, we cannot find it, but individually we can find it. Okay, that way we can make prediction. So the model is not going to overfit. In a way, the prediction is going to be more appropriate. That way, it's not going to overfit. There is no guarantee, but it's going to be better than decision tree. Got it? Do you guys got the essence there? Should I explain again?
No, sir.
This is the importance of ensemble models. When your original model is not working, ensemble model will work because of this kind of flexibility. You are building models with subsets of data, either rows or columns. That way you will get more combinations. More combinations mean more possibility to make predictions.
All possible
combinations will get created.
That means we are throwing all the stones.
Sorry?
We are throwing all the stones, at least one.
Yeah. It is like this. When you have a team of people, and maybe in a team 10 people are there, all 10 can do a particular task, may not be, but some people can do some tasks and some people can do other tasks. If you match and create appropriate planning, right, you can actually achieve the task, achieve the result. That's how the model is working here. Altogether it is unable to predict it, but individually some are able to predict and some are not. So you are taking the predictions of some and trying to predict whatever. Got it? Yeah.
Corona, they are applying all permutation and combinations of possible medicines.
yeah.
In that, hydroxychloroquine and azithromycin combination is better.
Okay. Erythromycin generally works for throat infections.
Azithromycin, not erythromycin.
Okay. Azithromycin.
Azithro also same. It's for throat infection.
Combination is same, I think. Ajax, they call it. I think. The chemical is same, maybe. Maybe, I don't know. We don't know. We are not doctors. So generally for throat infection, the Ajax medicine works. It's an antibiotic. So, that's good. That's a good news actually. If medicine comes, right, we can come out and roam around. If medicine and vaccine is not